Hi, in this video, let's talk about how computers store data. We'll talk about binary numbers. Binary numbers are the systems that use ones and zeros to store data using computer circuits. So you likely know that computer circuits have either an on or an off value, which are represented in numbers as a 1 or a 0. Let's go back to your school days. Do you remember when your teacher taught you how to count by numbers that were greater than 100? We used things like expanded notation. So 8,473 can be written like this: 8,000 plus 400 plus 70 plus 3. The idea here is that decimal numbers have place values. So first of all, place values in decimals look like this. Each place has a 10 as a base, and then there's an exponent. So we could write this 8,473 in a different form. We could say that 8 is the thousands place, which is represented as 10 to the third power. The 4 is in the hundreds place, which is represented as 4 times 10 to the second power. 7 is in the tens place, which of course is 10 to the first power. And the ones place is really a disguise of 10 to the 0 power. Remember, in exponents, any number raised to a 0 gives you the number 1 as an answer. So understanding place value is critical to understand how binary numbers work. Let's look at an example here. So I have a binary number written on the screen, and I have the place values listed below. So each number that you see, either 1 or 0, falls into a specific column. So the first column is the ones place. It is represented as 2 to the 0 power. So when we say that binary is a base 2 number system, we're talking about the base of the exponential problem. So let's take a look at how we would compute this answer. So we see that in this example, there is a 1 in the second place. The second place is represented as the 2 to the first power. And the next number over we find is in the 2 to the third power. So what is 2 to the third power? It is 2 times 2 times 2. So we'll call that the eighths place. So really we have a first place, which is the ones place, the twos place, the fours place. What we have here is the eighths place. Look ahead. We have another 1 coming up. It's at 2 to the sixth power. So what is 2 to the sixth? Well, the answer is 64. So this number is in the 64 place. What's the last one then? It's 2 to the 7th. So double of 64, that's going to be 128. So to compute the answer here, we have to take all of the places and add them together. So 128 plus 64 plus 8 plus 2. If you add all those up, and if I did my math correctly, we come up with 202 is our number. So using place value is a way that we can calculate a number, even if it is not a base 10 system. So why did we pick a binary number system? It's because we have these gadgets that are binary computers. In the early days of computing, we had vacuum tubes, which would store a value in the computer's memory. So a vacuum tube is essentially like a light bulb, except it has a charge in it. So it is either a high charge or a low charge, high voltage or low voltage, on or off. And in the early days, these took an immense amount of space. So you can see here that we have 8 vacuum tubes in a row. Each of these represents either 1 or a 0, a bit. Let's switch over into a program written in C# that will give us an example of how this looks. So I am going to translate numbers into their binary value. I'm going to use this statement here, which is called convert.toString. And the numbers that I put in here are the integer value, which is going to run from 0 to 255 in a loop. And then the second is a base number. So we are using a base 2 system. So this will give us a count of all of the binary numbers. Let's see what it looks like. So here's the results of the program. You can see that we start our for loop at 0. So it says the decimal value is 0 and the binary storage is 0. So far so good. You can see the pattern starts to move along here when we get along to like 3 bits. So the number 111 represents the number 7. So if you were to add these up here, we have the ones place, the twos place, and the fours place. That's 4 plus 2 plus 1. So that gives us 7. Let's scroll down to see where we have the next bump up in place value. So that occurs down here at number 15 and 16. So you can see that 15 has the value of 1111. So add those together. You have 8 plus 4 plus 2 plus 1. So that gives you 15. If we want to represent 16, then we have to go to the next value down, which is 1 with 4 zeros. So the place that we're looking at is a 16s place. That's 1s, 2s, 4s, 8s, 16 place. So that's why we get a 1 followed by 4 zeros. Where's the next break going to occur? Or where does the next significant digit come in? So that would be double of 16. Let's scroll down to 31. 31 gives you the 11111, and then we have 32, which takes a new place value. So let's double that again. Let's go to 64 and see what comes up. So I'm scrolling down to 64, and sure enough, 64 begins a new place value. The number 128 should be next in our list. Let's scroll to that, and you can see that the difference between 127 and 128 is a significant value. And then we get to the end here, and what was the last item? So I got up to 254. Had I gotten to 255, we would have included all ones here. So this program here, as you can see, its purpose is to convert decimals into a base 2 value so we can see what those look like in ones and zeros. Now let's talk about storage units that are in computer's memory or on their disk drive. So we start off with the smallest here, which is 1 bit. That's a 0 or 1. 1 byte is the value of 8 bits. And then you can see we jump into kilobytes then, which is 1024 bytes. 1 megabyte, 1 gigabyte, 1 terabyte, petabyte, and exabyte round off the title of the all these different measurements. So 1024, where did that number come from? Well, that is another one of those doubled values. So 2 to some power, I think it's 9 maybe, will give you the value of 1024. So that kind of tells you what the number value is of each of these measurements, but let's get a concept of how big each of these are. So a bit is a true or false value, that's 0 or 1. 1 byte is 1 letter from your keyboard, so the letter A, B, or C. Then we have a kilobyte, which is 1 page of unformatted text. 1 megabyte is about a minute was worth of music or maybe a photo that you take. A gigabyte is maybe an hour of video, not the highest quality video, but a medium quality. Or a Word document that has a bunch of pictures in it. That's about a megabyte. 1 terabyte is the size of a kind of a typical hard drive in a computer. And so you could put a lot of things on 1 terabyte. You could fill up your hard drive with all of the episodes from famous TV shows such as Law and Order, The Simpsons, Family Guy, Friends, The Office. Take all those together and you have a terabyte worth of video. A petabyte is the next guy up, and this is starting to get into some major large storage, at least in our opinion. So you could take a video camera and record it 24/7 at pretty high quality video quality, and you could do that for 3.5 years, and you would fill up your 1 petabyte hard drive. Or you could take 4,000 pictures every day and do that for your entire life, and that would be a petabyte. An exabyte is about 11 million movies if they were in high resolution. The entire internet would handle hundreds of exabytes of data per day. And then finally at the very top is a zettabyte. So a zettabyte is a lot, obviously. It's about estimated that we have more than 30 exabytes of data stored on every device in the world. So that includes every phone and every computer and every server and every data storage facility. So we're in the astronomical range that's really hard for us to conceptualize. So as a programmer, you're going to be required to understand the differences between these types of storage units in your programming language. So that's what I teach is computer programming, and we have to understand the difference between integers and longs and floats and doubles. So let's take a look at how these are categorized. So in the first column, you find what's called integer values. So these are whole numbers. So int. So uint is an unsigned integer. So only positive numbers can be stored in a uint. So you can see the rest of them are long, shorts, and bytes and things like that. The floating points are where you would have fractions or decimal points. So decimals, doubles, and floats are different sized items for taking care of decimal numbers. The object data format is completely different than any of these, so we'll leave that for a future video. What is an object? What are objects? How do you program with them? In characters, we have two different types of data storage. A char is a single letter. A string is a bunch of chars put together into a sentence. And then lastly, we have logic, which is a Boolean variable. Now, essentially, you could store a Boolean as a single bit, a true or a false. In reality, I think they use maybe a byte. Let's take a look at two floating point numbers. So here's an example of a floating point number. It's a decimal. So this rounds off to the nearest penny, you might say. It's 9 cents. But if you were to look at a more precise value, if you wanted to go out to the tens of zillions of digits, this is going to require a lot of data storage. So many, many bits are going to be required if you want to have very precise numbers. So if you're working with currency in a program, you're going to want to have a pretty good accuracy here. You don't want to be rounding off things. Transactions are, kind of sensitive. And if you're obviously into scientific instruments, then this is where it really makes sense to have more precision. So compare the different types of storage and how you can use a maximum and minimum range for each of them. So a Boolean is the first row in our table, and it is simply a byte. It's going to be either a true or a false, so not much of a range there. A char and a byte are both ways to represent an 8-bit number, or a byte. And so we can go from 0 to 255 in that range. So a char is a letter. So in the ASCII character symbol table, 65 has been assigned to the letter A. So whoever got to assign that first picked 65. For a lowercase a, the number is 97. So there is a key that corresponds between letters and numbers. So chars and bytes are really the same thing, but are interpreted differently by the computer. A short is a double length thing. It's 2 bytes. And you can see that the range here goes from a very narrow range, really, negative 32,768 all the way up to positive 32,767. So the negative sign takes one of the bits, and then the remainders are used for the numbers. You can see ints are much bigger, longs are huge, floats are like massive. So with the precision comes a cost. So really the cost is the memory usage. So if you're using longs for everything, you're wasting memory, because if your values of your game or your program never exceed the limits of an integer, then really there's no reason to use a long. So let's switch back into Visual Studio. I'm going to show you some examples of using these numbers, such as an integer and a short and a float. So the first thing I see here is a variable called score, and I've set it to be 32,768, which we're going to see why is significant in a minute. But the range of this integer is quite large, so we could do up to 10 to the 9th power of place values. So that's in the billions. However, the short value you can see here is only up to 32,000. So shorts have a pretty small limitation. And then we're going to work with the difficulty level here in the game, which is going to be a decimal of 4.2. So let's scroll down a bit now, and we're going to see that when we try to convert from one to the other, we get a problem. So if I say short score is now going to be equal to score, this doesn't work. However, the reverse should work. I'm going to comment out the other. So we can convert score from short score. So we can go from the smaller value into the larger without any trouble. However, we cannot go the reverse. So we will lose some significant values of what's going on here. So in other words, we have a limitation of storage. Now we can fix this problem if we do something called casting. So I'm going to put a parenthesis in here, and I'm going to put in the word short, which is going to say that we're going to take score and we're going to convert it into a short value, which then allows us to assign it to the type called short score. Now we could have some problems with that, and we'll find out in just a jiffy what those problems are. So let's change score to something like 9,000. So it's a fairly typical number. It's not outside of any range of anything. And then we're going to print both of these. So I'm going to say score equals, and now short score equals something. They probably look a lot like each other. They should be identical value. So when I run the program, sure enough, I get the value. It says score equals 9,000 and short score equals 9,000. No problem. Now the problem will occur if I try to go beyond the range of what the short score is. So let's go right up to the edge of it, 32,767, and run the program. This should still work. So we can see the results are that the score and the short score are both the same thing. So no problems with that conversion. We will encounter a problem if we try to go outside the range. So remember, the maximum value of short score goes up to 767. What happens if we push it just one beyond that? We're we're going to go to 768. So now we're out of bounds. Will the program crash? Let's find out. So you can see that the program did not crash. Instead, it switched this into a negative number. So the way that the numbers are stored says that the most significant bit in the value is a 1 or a 0, which is for the sign of the integer. And so by pushing it beyond the boundaries, we have turned the positive number into a negative. So this wraps around to the opposite end of the number line. And so you can get some pretty strange results if you go outside the boundaries of a short. Now let's try another conversion. I'm going to take the float value, difficulty, and try to store it into the score, which is an integer. Obviously, we got a red line here. We got a problem. It says you're not allowed to do that. So did you want to try a cast? So I'm going to say show potential fixes, add the explicit cast, and now it's doing a integer. So can you convert a float to an integer? Well, you can if you make some assumptions, like we're going to chop off the value of the decimal point and just give you the integer part. Let's see if that's what happens. So let's put a print statement in, first of all, that says, hey, we're going to print the difficulty first, and then we'll show you the score and the short score. As a matter of fact, I'm not interested in short score anymore, so I'm just going to comment him out. Let's go ahead and run the app. So you can see the results at the top. It says difficulty was 4.2, and when we converted it into score, it was an integer value of 4. What happens if I try rounding it to a different number? So let's go to 4.9. So will it round it up to 5? As you can see, the result is still 4. So doing a cast into an integer is called a floor operation. In other words, it always rounds it down to the nearest integer. So it is possible to convert from a floating number into an integer value. However, you're going to lose the decimals and you're going to round off to the nearest lowest integer. So now that you've seen some ways of how numbers are stored, let's talk about how storage has actually changed over the years. So here's an example of a memory card you could have bought in 2005 and one that was in 2014, probably for about the same price each way. One is 1,024 times larger than the other. So gigabytes and megabytes are obviously different scales, and we've grown accustomed to streaming videos and downloading huge files. Let's compare the different storage items that are in a binary system. So way back in the beginning, as I mentioned, we have these vacuum tubes. Then later in the 50s, we transitioned into transistors, which are much smaller, but they still hold charges, ones and zeros. Then we've come a next generation up, which is integrated circuits, and then microchips, which have grown smaller and smaller, more complex, using less power and more efficiency. So there's different ways to arrange microchips together. So we're all familiar, hopefully, with the CPU idea. CPU is the largest and most complex of the memory chips that are in your computer. However, there are others, and they're all designed to do different things. But the idea of integrating everything on one circuit and making a gadget that looks like a small cockroach is the idea of making simpler and more cheaply when you're trying to manufacture a computer. So we've shrunk the size of our storage over time. So the number of transistors that were in the 1950s were somewhat better than the vacuum tubes, was greatly improved, but we've kept up that same improvement on generation after generation, after what's known as Moore's Law. So Moore's Law is the idea that we noticed, or Mr. Moore noticed, that the Intel Corporation was cramming more things into smaller spaces. About every 2 years or so, they would double the number of transistors that they could put on a microchip. So that is possible because they have smaller and smaller gaps between the wires and the pathways and the transistors that are in their integrated circuits. So way back in 2002, they had 180 nanometers of space between items on a chip. So a nanometer is a 1/1000th of a meter. Very small. You need microscopes to be able to detect this kind of thing. We're getting down to the size of almost molecules and atoms on a chip. And as you can see, we've gotten smaller and smaller. However, you get to the top of the graph and you can see that the exponential growth has leveled off. We're still getting smaller, but the physics are getting harder and harder to overcome. And so in 2015, there was a 16 nanometer manufacturing process. Currently, 2021 is when I'm making this video, a 5 nanometer process is considered state of the art. And so they've shrunk it even further. So we're getting to the point where instead of using tools to do the etchings or the making of the chips, we're into light waves and X-rays and gamma rays and small little changes in the actual molecules of the substance that we're working on. So very, very small means less power and faster response times. Now, if you're one of the students in my programming classes, I'm going to eventually assign you the temperature conversion app. It'll be a very simple app, and it will use integers and floats and the conversion between the two using temperatures, such as Fahrenheit, Celsius, and Kelvin. And so that's a different video, but I invite you to stick around to join me for class. If you're not one of my students, please continue to watch and welcome aboard.